So hope you understood the numericals of the year. So we are going to see 2-3 applications in detail. It's not possible to cover all the applications in detail, but we'll see few of the applications in detail. So one of the application is FM detector. Now this is the block diagram for FM detector. Now if you look at the block diagram, can you see the resemblance with the block diagram of PLL? Yes, it is actually PLL. So if you have phase detector, then low pass filter, then error amplifier, then VCO, everything is in place. So I have marked this block, okay, as a dotted. So everything inside the dotted is actually PLL. So what we have done? So we have just used a capacitor here, coupling capacitor here at the output of error amplifier, and we have derived the output as unmodulated or demodulated output. So not unmodulated, it is demodulated output. So in PLL, if we give the input as FM signal and lock the PLL on FM signal, what is locking the PLL on FM signal? Locking the PLL on FM signal means PLL will track the changes in the FM. Okay, so if we lock the PLL on FM signal, the demodulated output of PLL is always going to be detected output for the FM. So you need not do anything, really we don't need any connection. Okay, VC output is already given to the phase detector, so it is closed loop. Okay, only thing is that we have to give the FM signal here. Don't forget VCO frequency. While setting the free VCO frequency, you have to take care that free running frequency of VCO must be equal to the carrier frequency of FC, carrier frequency of FM signal. I repeat, VCO free running frequency must be same as carrier frequency of FM signal. Because in FM, we change the frequency of carrier according to the modulating signal. So it will be shifted around FC, that is carrier frequency. So here care must be taken that VCO free running frequency must be set equal to carrier frequency of FM. Let us go through this quickly. So when PLL is locked onto FM signal, that means its VCO frequency must be around carrier frequency, which I have already told you. Then what happens when PLL tracks the FM signal and phase detector output? So here the phase detector output will be directly proportional to the phase difference between frequency of FM signal and frequency of VCO output, as you see here. In a way, it is proportional to the modulating signal. So recall in FM, I have already discussed, in FM, we change the frequency of carrier according to the modulating signal. So when we extract the phase difference or when we lock the PLL on FM signal, we track the changes in the carrier frequency. So output which is detected here as a phase detector output, and then to low pass filter, whatever the control voltage that we obtain here, that is proportional to the carrier frequency, changes in the carrier frequency. In a way, it is proportional to the modulating signal. So that's the whole concept. So control voltage which drives the VCO will be directly proportional to the modulating signal. So thus PLL can be easily used as FM detector. So let us understand these quick equations through these quick equations. So this is how we express FM signal. Let us consider this Fin as a FM signal, which is carrier plus VCO into control voltage. So we change the carrier frequency according to the so try to understand why we have written this equation like this. Now, what is this equation? This is actually F out equation, carrier plus K VCO, that is gain of the VCO and control voltage. So this is coming out of the VCO. Under locking condition, we make this signal and this signal exactly equal. So in a way, I can express F in as F out. And that's why we got this equation as F in is equal to F carrier plus K VCO into V control into T. So remember here, VCO frequency, pre-running frequency is set as carrier frequency. This is must. But actually how we define the FM signal? This is how we define. So it is carrier frequency plus changes in the carrier frequency as a function of modulating signal. So this is how we define as a FM signal. So here you can equate these two equations, and this is how we can write the equation for control voltage. So simple mathematics is there. So we go through this. So control voltage we can write as delta FC into sine of omega mt divided by K VCO. So as you see here, now this K VCO is fixed because this is a internal parameter of VCO, gain of the VCO, transfer function of VCO, which is fixed. Okay. So control voltage is directly proportional to the modulating signal. This is how we can use PLL as a FM detector. Let us see another application of PLL, which is AM detector. So before actually implementing this concept using PLL, let us understand in general how the AM detection happens. So conceptually, you can see here that we give the modulating signal. This signal is FM signal actually. So we give the FM signal here, and there is a local oscillator which also generates some signal. So there is internal multiplier which does the multiplication, and then we have low pass filter which actually demodulates the AM signal. So let us see this mathematically. So this is how we define the AM signal. So this is the AM signal. Recall, in amplitude modulation, we change the amplitude of the carrier. So this is voltage we are changing as a function of modulating signal. So we are modifying the amplitude of the carrier signal, which is Vp, by this amount. This is a modulation index, and we are modifying this signal amplitude, carrier signal amplitude, as a function of modulating signal. So this is how mathematically we define AM signal. Then once we add the local oscillator as a sine of omega ct plus theta, so omega c is the frequency which is equal to the carrier frequency. So if we somehow generate the carrier frequency through the local oscillator and then multiply the input, then this will be the multiplier output. So very simple mathematics is there, just go through this. So VOT will be multiplication of this and this. Okay. So if you multiply this by a sine omega c t plus theta, so what you get is AVP into bracket 1 plus mt sine of omega ct plus theta into sine of omega ct. So this is local oscillator frequency omega c, which is maintained as carrier frequency. So we can easily rearrange this equation and simplify this equation as AVP, and for this term you can write as cos theta minus cos 2 omega ct plus theta divided by 2. So as you notice here, there are two components. One is 2 times WC, one is 2 times WC. So this is high frequency component, this is low frequency component. Okay. So later when we give this signal to the low pass filter will allow only low frequency component and high frequency component will be blocked. And that is why VO at the output of low pass filter we get this as this. So if you see the equation, it is simply a modulating signal. Of course, it is phase shifted, 90 degrees phase shifted, but this is a modulating signal, right? So let us implement this concept now with the help of PLL. So just remember this block diagram. We are going to implement this. So how we do it? So notice that we have given AM signal as it is, but it is given through phase shifted. The reason is when we use a PLL, the output of PLL is always 90-degree phase shifted. So when we give AM signal and use PLL as a local oscillator, so VCO output will be 90-degree phase shift. So to match the phase, we deliberately introduce 90-degree phase shift here, so which we have not shown here. And then we have multiplier block and low pass filter block. So what is that we have added here? So we are using PLL as a local oscillator. That's it. So conceptually, the block diagram is very simple. So we have multiplier block, we have low pass filter block, and then we have used PLL as a local oscillator. So how PLL generates the local oscillations, that is this, which is equal to carrier frequency. It locks on the AM signal and tracks the carrier frequency and generates output equal to the carrier frequency. A very simple concept. But while doing that, it adds the phase shift of 90 degrees, and that's why to handle this, we have to add the 90-degree phase shift in the other path also. So this is the block diagram of AM detector using PLL. So let's conclude. So if the PLL is locked onto carrier frequency, so if this PLL is locked onto carrier frequency of AM signal, that means its VCO frequency must be around carrier frequency of AM. So VCO frequency of this PLL we have set to carrier frequency of AM. So PLL will track the changes in the carrier frequency so that output frequency will be exactly equal to the carrier frequency. So PLL tracks the AM. But VCO output always will be same as carrier frequency in this case, but don't forget this is unmodulated. So pure carrier you will get it. And since you are getting pure carrier here, we can consider PLL as a local oscillator. Recall that under lock condition, PLL output is 90-degree out of phase. So as I told you, this is 90-degree out of phase, and just to match this 90 degrees phase shift, we have to deliberately pass the AM input through the phase shift network of 90 degrees. And then we give the output to the multiplier. So multiplier does the rest of the part. That multiplier output is, as we have seen, it has two components, and that's why we pass through low pass filter. Low pass filter will remove the high frequency component and will average out the low frequency component to give the output voltage which is proportional to the modulating signal. So this is how we use the PLL as a AM detector.